Today's topic is called thermal equilibrium. So what we're going to start thinking is that the idea that when you put heat energy into a substance, you heat it up, which means its temperature rises. So that is something that I think we all know, we have clear in our heads, but that now we're going to measure it by how much temperature changes if you put in a certain amount of heat. So what we know is that if you put heat into something, so you give heat to a substance, that means that its temperature increases. Temperature increases. And the same thing happens if you take away heat from a substance. So if you take away heat, its temperature decreases. So an example of this first one is when you have water on a pot and you want to boil it. You put it on the stove, you turn on the heat, and this heat is energy that you're transferring to the water. And as you transfer more and more energy, the higher its temperature will get. So it'll start at an initial temperature Ti or T0. You can call it whatever you want. And depending on how much heat you put into it, the temperature will change. But as I told you on the first class, it doesn't only depend on how much heat you put into it. Because if you have the same heat, for example, a burner, a fire that's this big in your kitchen, and you put a stove of water that is this big, well, you're going to be able to boil it in a couple of minutes. But what if you put a whole pool? Imagine if you put underneath a pool of water that same burner that is this size. You probably won't be able to heat the pool very much. The temperature won't change that much. So one of the things that affects how much heat you need to change the temperature of something is the mass. So this temperature increase or decrease depends on mass, and something else. So mass is one of the things, and the other thing is the material. So it's harder to heat some materials than other materials. For example, to heat up metal, you don't need that much heat. You put a little bit of heat and you put a spoon near it, and the spoon will get hot really quickly and you'll burn your fingers really quickly. But as we talked about last class, if you try to heat up wood, it's going to be a lot harder because wood is harder to change the temperature of. So you need more heat to change the temperature of wood the same amount than metal. So it depends on the mass of the object that you're trying to heat and on the material that makes up the object, the material. So like last class, the material is determined by a constant. And this constant is going to be called specific heat. So the material is put into an equation through a constant called the specific heat. Specific heat. And it's given the letter C. C is the specific heat. So you can see that we have another table again here on the right, which has a list of common materials that people sometimes want to change the temperature of, and the C. So it has numbers. Water has a C, a specific heat of 4,186. Ice has a different specific heat of 2,100, so this is liquid water. We also have iron and steel, which have a specific heat of 450. And you can get from this list the specific heat. But what does it mean? Like, where did those numbers come from? Well, the specific heat is actually the amount of energy you need to raise 1 kilogram of each of those substances by 1 degree. So I'll write that definition here. So specific heat is the energy required to increase temperature T by 1 degree Celsius if you have 1 kilogram of the substance. 1 kilogram. So that is why the unit, if you look right there, is in joules. Let me write that here. So the unit of specific heat is in joules per degree Celsius times kilogram, or kilogram degree Celsius, because it's joules is energy. We saw that last year. So how much energy you need per degree to change by 1 degree, 1 kilogram of the substance. So what does it mean that water has a specific heat of 4,186? That you need 4,186 joules of energy to change 1 kilogram of water's temperature by 1 degree Celsius. And silver, you need 230 joules of energy to change the temperature of 1 kilogram of silver by 1 degree Celsius. So that's what specific heat means. Represented by the letter C, and all of the ones that you're going to need for the problems later are in that table. But if you require for another material, you can just look it up online. And you're going to find all of the C's there. Now, so this C is going to be useful for an equation that relates to us the heat that you need to change the temperature of a material or of a substance. So that equation, which is very common, I think, even in movies and everything, I don't know why. I think it's in Mean Girls, maybe. The equation is Q equals M times C times delta T. So what are these things? Q is heat. I think it's, along with C, the only new letter that we hadn't given a letter to. So Q is heat, and it's given in joules. Heat, as we saw in the first thermodynamics class, is just energy. Energy that changes the temperature of things. So heat is called by the letter Q, and it's given in joules. The second thing, M, is a mass. Mass. And it's given in kilograms in this equation and in most equations in physics. C, we have it already here. C is the specific heat with the unit joules per kilogram degree Celsius. And delta T, like always, is change in temperature. Change in temperature. So remember, change in is always final minus initial. So this delta T is exactly the same as writing in parentheses final temperature, TF, minus initial temperature, TI, right? So what we have here is an equation that is relating all of these things that we've talked about. Q, so that means how much heat you need. So if I ask you how much energy or how much heat do you need, you're going to find Q. And what does it depend on? It depends on the mass. So how much you want to heat up, if you want to heat up a giant pool of water or just a little pot of water. C, which is what do you want to heat up. If you want to heat up water, it's different than if you want to heat up wood. And delta T, by how much do you want to change its temperature. Was it initially at 10 degrees and you want to heat it up to 90 degrees? Or do you just want to heat it up 1 degree, maybe from 85 to 86 degrees? Yeah, so those are the three things that you put into the equation to get the heat that you need. Of course, you can, as always, use algebra to rearrange this equation. If you want to find the change in temperature, then you can grab these two, which are being multiplied to the change in temperature, and pass them to divide. So if I ask you, what is the change in temperature of water? So what is the change in temperature of water? If I give it an energy Q, and it has a mass M, and the C is the C of water. So you pass these two to divide, and you do Q over M times C. So what's the temperature change? The heat that you put into it over the mass over the specific heat. So that's how you use this equation. now I'm going to introduce a second topic, a second, well, concept very related to this. So I'm going to erase this part here. But of course, you can always come back and check it and see if it fits here in the middle. Okay, so now there is the concept that gives the title to this lesson, which is thermal equilibrium. So what does that mean? This was all talking about one single object. But what if you have two objects? What if you have a pot of water and inside you put a block of ice, or a piece of wood, or a piece of glass? Or you have steam, and in the middle of the steam you have iron or copper. So it just means, what do you do when there's more than one object? What happens is it's going to reach thermal equilibrium. So thermal equilibrium, the words mean something to do with temperature, and equilibrium means that it reaches a stable point. So thermal equilibrium means that all of the objects reach the same final temperature. So thermal equilibrium is when all the objects reach the same final temperature, or all the substances or everything you have in your system reach the same final temperature, and this temperature is called the equilibrium temperature. Final temperature, equilibrium temperature, final temperature, or just TF for final, which is the same that we were talking about right here, the final temperature. So let me see, thermal equilibrium, all the objects reach the same final temperature TF, and they have different initial temperatures. For example, you have your pot of water and it's at a temperature of 45 degrees, and you put in an ice cube, and the ice cube is at 0 degrees, and you want to find when the ice melts, because of course it'll melt if it's in a pot of hot water. When the ice melts, what temperature will the mixture have? And both will have the same temperature. So there are two things that sort of stay the same in thermal equilibrium. So one is the final temperature. Both objects will have the same final temperature. And the other concept in thermal equilibrium is that all of the heat that one of the things of the objects loses is going to be gained by the other object. Yeah? So what we're talking about is this isolated system, or this perfect situation in which no heat is lost to the surroundings, no heat goes out of the pot. Yeah? So we call that an isolated system. Isolated system. Which just means that we don't allow any heat to leave or enter the system, or the group of objects, from the surroundings. So no heat enters or leaves. So what that means is exactly what I just mentioned, that all of the heat that goes out of one object is going to be received by the other object. In the case of the pot of water with the ice cube, all of the heat that the water loses is going to be gained by the ice cube. So we can basically write that as an equation in which the heat, which remember we wrote as Q, the heat lost by one object is equal to the heat, Q, gained by the other object. So those are the two basic concepts of thermal equilibrium. Both objects will have the same final temperature, and all of the heat lost by one object will be gained by the other object, or objects, if there's more than just two objects. All the heat lost by all of the heat gained by the objects will be lost by other objects in the system. No heat will just go out into the surroundings. In a laboratory, because this is in a perfect circumstance, but that doesn't really happen much in real life. In the laboratory, we call this isolated system a calorimeter cup. Maybe you've seen that in chemistry, calorimeter cup. I could have shown you these in school, calorimeter cup, because they are just cups that are made from a material so that no heat leaves the cup. So maybe the most commonly used type of cup or object that is close to a calorimeter cup is a styrofoam cup. Styrofoam cups, if you grab them, your hand doesn't get that hot. That means that the liquids inside aren't losing that much heat to your hand. So calorimeter cups are just that, are cups that no matter how hot or cold the thing is inside, if you grab it with your hand, you won't feel the temperature because the things inside aren't losing or gaining heat. Also, like these bottles that they sell, like the thermos bottles that keep the liquids inside hot or cold, those are basically calorimeter cups. So you'll see that in the problem, and it just means an isolated system where no heat enters or leaves, and when this equation remains true. Okay, so now after that introduction, what are we going to do with this to get an equation that we can solve to figure out the final temperature of a mixture of objects or substances? So now this part is maybe the part of physics that has more algebra, and I know you guys don't like that, but we need to do it. We need to practice a little bit of algebra, and it's not hard algebra. So Q is given by this equation. We saw it a while ago. But this is one object and this is another object. And one of the objects, the hot one, will lose heat and the cold one will gain heat. So we can rewrite this equation but put in the definition of Q instead of Q and solve the equation. So suppose we have our example of the ice cube and the water. So we're going to call the ice cube, our object 1. So it's our object 1. And the water is our object 2. Object 2. So what we have here is that the Q that object 1 will gain, because it's the cold one, so it'll gain heat, is going to be equal to the Q that object 2 loses. So because one loses and one gains, we're going to have a negative symbol right there, negative sign. And now these Q, we can put, instead of the Q, we can put the definition. So we have M, C, and delta T. M, C, and delta T. But these are of the object 1, not of both objects, or just of object 1. So in order to not get confused, we can put M1, C1, delta T1. That's this side of the equation. On the other side, we also have heat, but of the object 2. So we put the negative sign that we had, and we also put MC and delta T. But this time it's M2 times C2 times delta T2. And that's the equation that we need to solve. So we're going to be given a lot of numbers, masses, specific heats that we have already in our table, and initial temperatures, which will go inside of the change in temperature. And we're going to have to find the final temperature. So in the next video, I'm going to solve an example using this equation. But this is the general equation. That the mass 1 is equal to C1, mass 1 times C1 times delta T1 is equal to negative mass 2 times C2 times delta T2. And if you prefer to use this TF minus TI, you can put that in, and that'll work as well. So the equation, the long version of the equation would be M1 C1 TF1 minus, TF is the same for both, so just TF minus TI1 equals minus M2 C2 TF minus TI2. And the only thing that you need to do is, having this equation, you plug in every single value that is given to you in the problem, and you solve for whatever is missing, which is generally just one thing. So that's where the algebra comes in. But that's the general equation. If you have more objects, you put another MC delta T. So maybe it's another hot object that will lose heat. So you put another negative here, and you put your M3 times C3 times TF. Still, no matter how many objects there are, there's still only one TF times minus TI3. So that is the definition, the introduction, and the equations for thermal equilibrium.